has a practical associated with it, and I'm also going to demonstrate the practical and how you might go about answering some of those questions that have been set. So we've got an investigation here. It's a hypothesis which says that the temperature change in a displacement reaction depends upon the reactivity of the metal. So a quick recap of our reactivity series: potassium, sodium, calcium, magnesium, aluminium, carbon, zinc, iron, tin, lead, hydrogen, copper, silver, gold. And don't forget, hydrogen and carbon are always in italics or brackets. They are not metals, but they can be used to extract metals, more reactive than some of the ones below it. So before we actually look at this practical, I'm going to sort of like just go through a couple of things with regards to variables. All right, it's the how science works process. So any sort of investigation will have an independent variable and a dependent variable. So the independent variable is the thing that you are changing. So what are we going to be changing in this particular experiment? So the temperature change in a displacement reaction depends on the reactivity of the metal. So hopefully you can see that it is the reactivity of the metal, therefore the type of metal, that we are going to be changing. So I'm going to be changing the type of metal, therefore the reactivity of it, because different metals have different reactivities. And I'm going to now look at the independent variable. What will I be measuring? So again, you should be able to get both the independent variable and the dependent variable from the hypothesis. So if I'm going to be measuring, sorry, if I'm going to be, changing that, that's the independent variable, so, sorry, okay, do apologise. That's what we're changing, that's the independent variable, is the reactivity of the metal. The dependent variable is the thing we're going to be measuring. So we're going to be changing the reactivity of the metal each time, and you can see that in my results table. I've got the metals just there. So what are we going to actually be recording? Well, we're going to be measuring the temperature change in a displacement reaction. So that is our dependent variable. So we're changing the type of metal, therefore the reactivity. We're measuring the temperature change in a displacement reaction. All right. So how are we going to do that? Well, I've got here a bottle of copper sulfate, and copper sulfate contains copper ions in it. So we've chosen these four metals here: aluminium, magnesium, zinc, tin. So if I just identify where they are in the reactivity series, so copper is there. We're starting off with copper sulfate. Do these four metals have enough reactivity to be able to displace copper from copper sulfate? So we're making sure that all four of these are above copper in the reactivity series. So tin is there, zinc is there, magnesium is there, aluminium is there. So that's what we should be able to see a reaction take place. And we're asking whether or not that the temperature change, so the temperature will go up in these reactions, is dependent upon how high the reactivity series is. And hopefully you guys come up with your own sort of theory or prediction with regards to that. Do you think that the more reactive the metal, the higher the temperature change? Or do you think the less reactive metal, the lower the higher the temperature change? So again, you can make your own prediction based on this. So if you want to just take a few minutes to think about, do you think that the temperature change of a displacement reaction will depend upon the type of metal or the reactivity of the metal? And if so, do you think that the more reactive metals will give a bigger temperature change? Or do you think the less reactive metals will give a bigger temperature changes? And this is the whole point about science. You make a prediction, yeah, and it doesn't matter if your prediction wrong. If you make a prediction because you've got your own ideas, brilliant. You're a scientist, you're a chemist, well done. And if it proves that your prediction was wrong, who cares? You've learned something, right? You've taken part in the scientific process. Okay, so I'm going to be mixing all four of these metals with samples of copper sulfate. Yep, so there's our copper sulfate. It's unmistakable blue color. Let's just use magnesium. Okay, so what we're saying is going to happen here is that copper sulfate to make magnesium sulfate and copper. Yeah, so all we're actually doing is we're swapping or displacing the copper for the magnesium. And according to the reactivity series, magnesium is more reactive than copper, so it will happen, right? Just give you a bit more chemistry though as to what's going on here, all right? Because even though we don't cover this until we're in sort of like year 10, year 11, I thought it'd be a good time to introduce it. What's actually happening to these particular atoms and ions? Well, we've got copper 2+ in copper sulfate. That copper ion is going to become copper atoms, all right? Because we've got copper 2+ there, because it's bonded to a sulfate ion, and we've got copper atoms over there. So we've got to think, what is happening to our positively charged ion to become an atom? Well, think about it in reverse first. If I wanted to get lots and lots and lots and lots of these, what needs to happen to a copper atom? So if I want to go from there to there, the copper atom will need to lose 2 electrons to become a 2+ ion. So if it's going back the other way, right, here's how we represent it, we show that the copper ion is gaining 2 electrons. So what's happening in these reactions, and we're just using magnesium as an example, aluminium will do the same, zinc will do the same, tin will do the same, because they are more reactive, right? The copper ions are getting 2 electrons from the more reactive metal. So again, let's look at what happens to the magnesium. So the magnesium becomes Mg2+. And again, we do a whole topic on these types of Hard equations. So what's happening in these displacement reactions, it doesn't just happen in these particular ones, it happens in all kinds of displacement reactions, is that the more reactive metal is losing electrons. So this thing here is losing electrons. And then hopefully you can see those electrons are being taken in by the less reactive metal. So the more reactive metal is losing electrons, and the non-reactive metals, or the less reactive metal, is gaining them. All right, and there's 2 very specific terms I'm going to introduce you to here. If it is gaining electrons, we call that process reduction. And if it is losing electrons, so the more reactive metal, so I'll just put there, more reactive loses electrons. So you can see we represent electrons with an E to the power minus. So E is for electrons, and a minus is to let you know that it is negatively charged. So the more reactive metal is losing electrons, we call that oxidation. So there's 2 new terms there, which I'm introducing to you. If you're in year 9, if you're in year 10, 11, you should have come across these before. So that, all right, well, hopefully this will make a bit more sense to you. So never forget your oil rig of electrons. Very important in chemistry. Make sure you know about your oil rig of electrons, and this will help explain what that actual acronym stands for. So O is for oxidation, is loss. Just check. Was oxidation losing electrons? Is this thing losing electrons, giving up electrons? Yes, it is. So it is oxidizing. It is losing 2 electrons. And then reduction is gain. All right, and just check our reduction equation is this one. Is this gaining electrons? Is it adding electrons to it? Hopefully you can see it is. So the more reactive metal is losing electrons, and the non-reactive metal is gaining them in displacement reactions. It's a good thing to sort of, you don't have to fully understand it yet, but I'm introducing those concepts to you now. All right. So let's have a look at the actual reaction then. So we're changing the metal, we're measuring a temperature change. So again, let's have a look at the actual practical, and I'll see if you guys can't make a list of, let's go slightly off piece. Yeah. Okay, so think about what things we're going to keep the same. Okay, so Okay, so I've got my 4 solutions here of copper sulfate. And one thing you can hopefully notice about each one is the volume. Okay, so the volume of the solution stays the same. So I think in your question that I've given you, you've been asked to give 3 control variables. Volume of solution or volume of copper sulfate solution is obviously going to be quite important. All right. So you've got volume of solution. Yeah. What else do you think needs to stay the same? Well, I'm going to start putting these different metals into the 4 different conical flasks. So start thinking about what needs to stay the same about the metal. Is there anything specific that needs to stay the same? All right. I'll let you think about anything else. Anything else about this practical. So I'm going to be measuring the temperature change. I've got some copper sulfate solution and I've got different metals. All right. Start typing them into the chat and I'll see if anyone can come up with any of them. Hi, Molly. Oh, Lewis. And Lacey. Right. So hopefully, if we're keeping the volume of the solution the same, what do we need to keep the same about these metal powders? Hopefully, you've got the idea of it's going to have to be mass, right? So solids, we always talk about mass of solid, not volume, not amount. We never, ever use the word amount. Amount is just too vague. So if you're dealing with liquids, go with volumes. Solids, masses. Yep. So you should keep the mass the same. Anything else you should keep the same? Maybe the starting temperature. Do you think the starting temperature will make a difference to how high the temperature will go in all 4 of these reactions? Probably will. And one more thing as well. Just going to sort of show you the bottle there. It says 0.5 m copper sulfate. So what does the 0.5 m stand for? That stands for the concentration. So you need to ideally keep the concentration the same. It's basically the amount of copper sulfate dissolved, sorry, the mass of copper sulfate dissolved in a certain amount of water. Right then, so first thing I'm going to measure is the starting temperature. So to make sure these are all the same, they've just been sat in the same lab for a while now. So that's reading 19. That's reading 19. Yep, and would you believe it? They've all been sat at the same desk in the same lab. Their starting temperatures are all the same. Yeah. Okay, weigh specific masses of these metals, but I'm not going to do that, all right, because time. So I'm just going to put about a spatula of each metal into, and then we'll see what happens. So this is my zinc, maybe a bit more, and the final one is tin. And this is actually the only time I'll allow you to say this, because it's actually what it says. This is tin foil, yeah, not the stuff you get from supermarkets, which is aluminium foil. So let's have a look then. If I just start swirling these around, and I can see the temperature is going up. Yeah. Yep, well, that's going up quite nicely. This one. Yep. and this one. Right, so basically keep swirling them until you get a final temperature change. All right. Okay. All right. Good stuff. All right. Okay, so I'm going to record the data now, and I'm going to put it back into the table, all right, over here, and then we'll see what you can do to process those results. Obviously, I don't want you to process it. I want you to use this video to answer the exam question that I've set you. All right. Okay, so I'll bring you back over to the main platform. There we go. Okie dokie. So, what have we got here? Right, we can see that the tin has, so the tin has gone up to, the magnesium has gone up to about 20. And the aluminium has actually stayed at 19. Fascinating. So I can use these results to now work out a temperature change. All right. Obviously, n is takeaway start. So that's gone up by 0. That's gone up by 8. That's gone up by 2. And that's gone up by 1. Yeah. So before we start looking at that question about the graph that you've got, does the reactivity of the metal affect the temperature change in a displacement reaction? Can we draw a conclusion from this? You could, yeah, there is a trend, all right, that, you know, the most reactive metal was magnesium. So magnesium is most reactive. And it gave us the biggest temperature change. Yeah. However, at the opposite end of the scale, did the least reactive give us the lowest temperature change? Well, no. Actually, aluminium gave us the lowest temperature change when in reality, it should have given us the second biggest. So it should have been, you know, just less than magnesium and above zinc, somewhere in there, if this hypothesis is absolutely perfect. Well, it's a bit of a false result, this 0 degrees Celsius. Yes, it did not go up. The temperature did not go up. But can we think as to why that is? The temperature should have gone up. It should have gone up by, according to these results, somewhere between 8 and 2. Yeah, that'd be perfect for aluminium because it's between magnesium and zinc. So why didn't it? Why has the temperature not gone up in that reaction? Any ideas, any thoughts as to why it might be? Just type them into the chat and we'll see what you come up with. The suspense. The reason why the aluminium is because it wasn't probably aluminium that was reacting. Because aluminium is one of those really reactive metals, right? Just like magnesium. But it forms a protective layer when it reacts with something in the air. And that something is called oxygen. So when aluminium reacts, right, as soon as it's exposed to the air, it reacts with something called oxygen to make aluminium oxide. So if you imagine a drinks can, for example, drinks cans are made of aluminium. Yeah, they're made on the production line, pure aluminium. But as soon as they're exposed to air, what you get, so imagine this is my drinks can of pure aluminium can, is that the oxygen starts reacting with the atoms, and you end up with this very thin layer, aluminium oxide. So it's a thin layer. of aluminium oxide. So it's the thin layer of aluminium oxide which is coating the aluminium, which is stopping the rest of it reacting. So imagine this was our piece of aluminium that we put in the solution. Well, if it's got a thin layer of aluminium oxide, which is fairly inert, i.e. doesn't react with much, then really all this aluminium on the inside is protected. It cannot react. And because it cannot react, there was no temperature change. So if you were to do it, if I was doing an evaluation on this, I could perhaps do some, I could do an explanation as to perhaps why. I could explain why that could be an anomalous result. We'll move on to one more thing then before we finish, which is how would you present this data? So you've got a graph, I believe, to draw in your exam question, and I recommend you do it on paper or just do it some sort of do it on Excel or any sort of like word processing platform. So how would we present this data? What type of graph would it be? So you're going to have temperature change there, or mean temperature change, because that's the dependent variable. Your dependent variable always goes on the y-axis. So y-axis is where you've put the thing that you are measuring. The thing that you are changing, i.e. your independent variable, always goes on the x-axis. So we'll put type of metal. Okay. So think your independent variable, all right, when you're plotting graphs, is like an apple. Yeah. It's the thing that you change and it goes on the bottom. Yep. So it's on the x-axis. So I know that's where the two axes are going to go. But I need to know what type of graph it's going to be. Is it going to be a line graph, a bar chart, or whatever? Well, the key thing is this is going to be a bar chart. So you're going to have aluminium, you're going to have magnesium, you're going to have zinc, aluminium, magnesium, zinc, and tin. Yep. You're going to do it as a bar chart, but why are you going to do it as a bar chart? Well, look at our independent variable. Look at what we are changing. We're changing the type of metal. Now, what type of variable is that? Is type of metal a number? Are these things here numbers? No. So it's non-continuous data. Non-continuous data means that it is not based on numbers. It's based on words instead. So, for example, the color of your hair. The color of your hair or beard, you would say is non-continuous because you'd say that your hair is blonde, your hair is brunette, your hair is black. Right? So you use words to describe that particular variable. If it was shoe size, for example, yeah, size 11, size 12, size 13 and a half, you would say it is continuous because you're using numerical data. So because type of metal is non-continuous, or you might sometimes call it categoric, as in it's described by categories, you always do a bar chart. So you got a question, I think, in your exam, or exam question as to why would you present it as a bar chart, not a line graph? It's because the independent variable is non-continuous or categoric, or described by words. And if I was plotting it loosely, so we call that 1, 2, 3, 4, 5, 6, 7, 8. This one would look like this. Zinc would be 2, and tin would be 1. Okay, it looks something like that. And they do ask you more and more these days to draw bar charts and graphs in your exam papers, and it's usually worth about 2 to 4 marks on each paper. So it's about 4% of each paper. So it's worth actually sort of having a bit of time practicing these. And they're quite nice marks to actually get. All right. So hopefully I've given you enough information there to be able to access to